Hello students, welcome to this lecture number 6 on the structure of the atoms. In this lecture we are going to discuss the particle nature of the electromagnetic radiation, or we can say the particle nature of light. This is K.K. Mukherjee in the Science with Mukherjee Sir YouTube channel. This video is basically very free from any type of cost. You can easily avail this video if you have the internet connection and have the smartphone. Completely free from any type of cost. So in this video, in the previous video, in the lecture number 5, we have discussed about the wave nature of the electromagnetic radiations. And this wave nature of the electromagnetic radiation, that is help us to explain lot of things, lot of properties of the light, like is the diffraction property, interference property. But there are some phenomena which is going to be explained by this wave nature of the light. So this can be explained by the particle nature of the light that we will discuss in this video. So today's video, heading of today's video is the particle nature of the light. So you can write this video, heading of this video is particle nature of the light. We discuss on the particle nature. And light is a form of electromagnetic radiation, and it is having, we will understand afterward, that is, it is having the dual nature. It is having the particle nature as well as the wave nature. So there are some phenomena which cannot be explained with the help of the wave nature of the electromagnetic radiation, or we can say the light. Those phenomena, number 1, the nature of the radiation emitted by the black body. Nature of radiation emitted by the black body. Number 2, the photoelectric effect. Number 3, line spectrum. Line spectra of atom. These 3 things could not be explained by the wave nature of the light. For this, you have to have this another nature of the light, that is we are going to discuss, that is the particle nature. And in the year 1900, Max Planck has put forward a very unique theory, and due to this theory he has been awarded the Nobel Prize in the year 1918. This theory is called the Max Planck quantum theory. This theory is called the The main points of the Max Planck quantum theory. Number 1 point, energy emitted or absorbed from the source discontinuously in the form of small packet of energy. That is the first point. Second point, the small packet of energy small packet of energy is called the quantum, and for light it is photon. Third point, the energy of quantum is directly proportional. The energy of quantum is directly proportional to the frequency of the radiation. That is, we can say, suppose E is the energy, then it is proportional to the frequency. Frequency, suppose nu, it is represented by nu. Then we can say E is equal to H into nu. H is the Planck's constant and it is given by 6.6 in 10 to the power minus 34 joule seconds. This is called the quantum, which is proportional to the frequency of the radiation of the electromagnetic radiations. So E is equal to H nu. That is the third point. And the fourth point, the energy emitted is 1 photon, because 1 quantum, or multiple whole number multiple. Which means E is basically N into H nu, where N equals to 1, 2, 3, not 1.5, 2.5, 3.5. So energy emitted is 1 quantum or whole number multiple of this quantum, whole number multiple of quantum. That is the main 4 postulates of the main points of the Max Planck's quantum theory. First, the energy emitted or absorbed from the source discontinuously in the discrete way in the form of small packet of energy. Small packet of energy is called the quantum, and for the light it is called the photons. The energy of the quantum, energy of the small packet is proportional to the radiation, frequency of the radiation. And fourth point, that is the energy emitted is 1 quantum or whole number multiple of the quantum. That is a very, very important point to understand. This is called the quantized energy. This is called quantized. The energy has been fixed. Energy never be a fraction, and energy is discontinuously spread from its source. That is the main points of the Max Planck quantum theory. Now we understand what is black body, ideal black body. Ideal black body is basically that is those body that which can emit or which can absorb any type of radiations. This is called the ideal black body, and the radiations made by this ideal black body or absorbed by ideal black body is the ideal black body radiations. So what is going to happen? That we will understand now. When we hit the black body, what is going to happen? That we will understand, and from that this wave nature has been not applicable for this phenomena. It will be the particle nature what Max Planck has been said. What is ideal black body? It is a ideal body which can emit or absorb all types of radiation the radiation emit or absorb is called the black body radiation. So we understand what is black body radiation and what is black body. Black body is capable of emitting every types of radiations, or it can capable of absorbing any type of radiations. This is called the ideal black body. What is going to happen? Suppose we hit a iron rod. Suppose we are hitting a iron rod. What is going to happen? We are hitting a iron rod. You will see practically that first it will emit a radiation that is having the frequency of the red light, means it will have the red color. So its color will change, you will find red, then you will find it is orange, then it will be yellow, then when it is sufficiently heated, then it is blue, or at the end it will be white, you can see. So with the time, as we go on increasing the temperature of the black body, it will going to radiate different types of the energy, different types of the frequency, which is having a different colors. That is the main point of the black body, and from this observation the particle nature comes. You cannot able to explain this phenomena with the help of wave nature, because in wave theory what is there? If you go by the wave theory, the energy content in wave theory, the energy content, you can see the energy content is proportional to the brightness of the color. Brightness content is proportional to the brightness, or we can say the intensity of the radiation, or you can say light. So if it is so, then when we supply energy to this heat rod, it will, with the increasing energy, the brightness of one color will change. We can say the brightness of one color will change. Brightness of one color. Suppose this is red. Will intensify. Means initially this is a dull red, then it will be a bright red, and so on. So in that fashion, if it is a wavelength theory, this type of defined type of radiation you will not be able to find out. So wave theory would not able to explain this phenomena that when we hit the iron rod, or you can say a black body, that its color has been changes with the time, and it is the function of the temperature. As the temperature is increasing, the frequency of the radiation is also increasing. You can say red is having the frequency, you can see, that is 4 into 10 to the power minus 10 to the 14 hertz. Then the blue, it is having almost 6 into 10 to the power 14 hertz. So you can see there is an increase in the frequency of the radiations. And if it is a wave nature, then this type of color change will not be there. It will be only the brighter. The radiation will be more brighter, but color will be same. Suppose this is the red, but this is not going to happen in case of the black body, which we are going to see practically that the color is changing. But this can be understood from the Max Planck quantum theory. Max Planck said energy is proportional to the frequency as contrast to the wave. Wave nature say energy is proportional to brightness or intensity. Energy is proportional to the Max Planck energy is proportional to frequency. So when we supply energy, more and more energy, the frequency will going to change. It is very simple. So E is equal to, we know, H nu. So as the E is increasing, H is a constant, then nu will be frequency of this increasing, and that is what is going to happen. First we will see red, it is having less frequency, then it is orange, it is slightly higher frequency, and this frequency goes on increasing, and you will see this type of things. You can also make a distribution of these things. Suppose you make temperature T, and in this case, this is a wavelength. You see the wavelength, and it is an intensity. So suppose there are two temperatures, that body have been heated in the two temperature. The temperature, initial temperature T1, it is less than T2. So frequency, you can see distribution will be with the wavelength will be like this. As a particular wavelength will be going to be increases in the temperature of T1. And when we increase the temperature, what is going to happen, you can see this will be like that. And here the wavelength, you can see that is decreasing, where this is T2. At a higher temperature, you can see the frequency of the radiation is goes on increasing due to this fact that it is at the particle nature. It is at the particle nature, and it is going to influence the energy of the radiations, because we are supplying the more of the energy to this black body. So that is the main thing, that wave nature could not able to explain this phenomena of the black body, and this can be only explained by the particle nature of the radiations. So I think that we understood to you. You can well understand. If you don't understand, you can make a comment on the comment sections. Now we'll give some numeric, some questions that it can clear your the concept of the electrode. Question number 1. Which is never true for the cathode ray? They possess kinetic energy, they are electromagnetic radiations, they produce heat, they produce mechanical pressure. Which is never true for the cathode ray? They possess kinetic energy, we know this because this is a particle nature, it is a particle, material particle. They produce heat because when it collide with the wall of the container, it is going to produce the heat. They produce the mechanical pressure, and this is not the correct thing. That is, cathode ray is not the electromagnetic radiation. Why it is not electromagnetic radiation? Because it is not created by electric field or the magnetic field. We know the electromagnetic radiation is going to be created when there is a charged particle has been oscillating, and it will going to create the electric field and magnetic field, and this electric and magnetic field will propagated and it will going to give you the electromagnetic radiations. But this type of things cannot happen in case of cathode ray. It is only produced from the cathode at the perpendicular directions. Second thing, why the cathode ray is not electromagnetic wave? Because electromagnetic wave is not having the particles, made of the particles. It is a particle nature, but it is made of the particles. But the cathode ray is made of the particles. So all those things that you can see, that cathode ray is never the electromagnetic radiations. It is basically the ray of the particles. The ray is basically made of electrons. Another thing, in the electromagnetic radiation, that is double in the speed of the light, but where the cathode ray never go to the speed of the light, it is having the 1/10 of the velocity of the light. That is another question that we are going to discuss. Question number 2. Which of the following statement is not correct? That is, energy of the photon is h nu, rest mass is 0, momentum of the photon is h nu by c, photon exert no pressure. Among these, this will be the right answer, because photon is basically electromagnetic radiation. When it interacts with any particles, it will going to transfer the momentum, and that you can observe. Next video we are going to discuss that is the photoelectric effect. So that is all for today's video. If you like this video, you can share with friends. I think it will be benefited to you, and you must enjoy this video. Thank you very much for watching this. Thank you.